Hello, students! Today we're going to learn about a differentiation technique called implicit differentiation, and hopefully this is notes number 27. So before we get into the technique, I want to talk about the meaning of the word implicit, and it helps to first talk about the meaning of the word explicit. Now, I'm not talking about explicit in terms of like rated R or rated X or something. I don't mean like bad language. I mean sort of a more general definition where explicit means something that's clearly expressed or communicated. So some visuals here. It's pretty clear the direction for failure and the direction for success. It's pretty clear which direction the man needs to walk. And then in terms of math, if you're talking about what is y, it's pretty clear in the first one that y is equal to 2x minus 4. And in the second one, it's pretty clear that y is equal to the sine of the cosine of 2x. So we're going to contrast that with implicit. A dictionary definition of implicit: something that is suggested or implied but not ever clearly said. So in these there's a bit of confusion. It's not very clear. And for the math example, if the question is what is y, well, in this first equation it's not clear. Now I suppose you could isolate y by going through some steps, but just by looking at the equation we don't know exactly what y is, and the same thing is true for the second one. And there will be other equations where we don't actually have the algebra skills to isolate y, so we wouldn't be able to do it even if we wanted to. So, what is implicit differentiation? Well, let's say you wanted to find a derivative, find dy dx. If you were given an explicit equation, you could do it directly. So let's take the first one. Dy dx is the derivative of 2x minus 4. That would be 2. Or in the second one, the derivative of the sine of cosine of 2x. It's going to take a little more work because we need to use the chain rule. So first the derivative of sine is cosine, so cosine of the inside, times the derivative of cosine is negative sine, so negative sine of the inside, times the derivative of 2x is 2. So we can do that. But what happens if you have an equation that's expressed implicitly? How do you find dy dx? So that's what we are going to learn today. And what we're going to do is kind of step through it from some really simple examples and build from there. So this is all based on the chain rule, where you have an inside function and an outside function. So let's say we have the expression sine of x quantity cubed. Now we would typically see it like this, the sine cubed of x, but just to make it clear, the inside is the sine of x, the outside is the cubing function, and let's say we're taking the derivative of all of these with respect to x. So x is our variable. If you see any other letter in any of these problems, that letter is a function of x. So we take the derivative of the outside, and that would mean we have 3 times the inside squared times the derivative of the inside. Now I could write that a different way and simplify it, but that's good enough for now. So let's look at something similar. In this case we have smiley face cubed. It's the same situation. We have an inside and we have an outside. So we first take the derivative of the outside. So we have 3 times smiley face squared. And then we have to multiply that by the derivative of smiley face. See, smiley face is not our variable. X is our variable. Smiley face is a function of x. So what's the derivative of smiley face with respect to x? That would be d smiley face dx. Or if you want to write it in a different way, and I'm going to go ahead and put my circle around the face here, 3 smiley face squared times smiley face prime. See, instead of writing d smiley face dx, we can write smiley face prime just as a shortcut notation so that it takes up a little bit less room. So let's say we have y cubed. It's the exact same thing as smiley face cubed. First we take the derivative of the cubing function, so that gives us 3y squared, and then we multiply it by the derivative of the inside. The inside is y, and y is a function of x, and the derivative of y with respect to x is dy dx. Or you can write it like this, 3y squared times y prime. You just have to make sure you understand that y prime is not the same as y to the first power. So we're not looking at y squared times y to the first, we're looking at y squared times y prime. Okay, here's the next one. Switching gears a little bit, the square root of 7x is the same thing as 7x all to the 1/2 power. So if we want the derivative with respect to x, again using the chain rule, we bring down the 1/2, and we raise 7x to the negative 1/2, and then we multiply by the derivative of the inside, and the derivative of 7x is 7. And then that could be simplified. So suppose we want the derivative of smiley face, square root smiley face. Same idea. This is the same thing as smiley face to the 1/2 power. So we take the derivative of the outside function, we bring down the 1/2, and we raise smiley face to the negative 1/2, and then we multiply by the derivative of the inside, and the derivative of smiley face with respect to x is d smiley face dx. And so we can write this as 1/2 smiley face to the negative 1/2 times smiley face prime, and we could simplify it too. We could get rid of the negative exponent and that kind of thing. So the same thing applies if you have the square root of y. So this means the same thing as y to the 1/2 power, and for its derivative we start by taking the derivative of the 1/2 power function, bring down the 1/2 and raise y to the negative 1/2, and then we multiply by the derivative of the inside, which is dy dx, and we can write it as 1/2 y to the negative 1/2 times y prime. And I'll go ahead and simplify this one. So we have the y prime, and then on the bottom we have 2 y to the 1/2, because I'm moving it down to change the exponent from negative to positive. And y to the 1/2 is the same thing as square root y. So y prime over 2 square root y. And then kind of combining a couple of these together, what if we have the square root of 7y? So this is 7y to the 1/2. So this one actually has 3 layers. The outermost layer is the 1/2 power function. So we have 1/2 times 7y to the negative 1/2 times, then the derivative of the middle layer is 7y, so its derivative would be 7, times, the inside layer is y, and its derivative is dy dx. So we have altogether 7y prime over 2 square root 7y. So if you look back at all of the examples that involved a y, which is what we'll typically have. You don't typically have problems with smiley faces in them. That's just my way of explaining it to you. Every time we had something with a y, there was a times dy dx, or a times y prime. That's the derivative of the inside function. Okay, we're going to go through a few more, and then we'll get on to the more complicated problems. So, what's the derivative of x with respect to x? Just 1. And you can even write it as dx dx, but it's just 1. You could think of dx over dx as like a fraction where it reduces, I suppose. But in general, we don't think of dy dx as a fraction of two things. We think of it as just one quantity, the derivative of y with respect to x. So, what if we wanted to find the derivative of y? Well, that would be dy dx, or y prime. What if we wanted to find the derivative of y squared? The outermost function is the squaring function. Its derivative would be, bring down the 2, raise the y to the first. I'm not going to write the 1. And then the inside function is y. Its derivative is y prime. So we get 2y, y prime. What if we want the derivative of sine y? The outside function is sine. Its derivative is cosine. So we have cosine y times, the inside function is y. Its derivative is y prime. Hopefully you're getting the idea now. What if we want the derivative of xy? Xy is a product, so we need to use the product rule. So we have the first times the derivative of the second, the derivative of y is y prime, plus the second, y, times the derivative of the first is x, and its derivative is 1. So we can simplify as just xy prime plus y. Okay, here's another product, xy squared. So again, we'll use the product rule. The first, x, times the derivative of the second. Okay, well, remember what we did up here. When we took the derivative of y squared, we used the chain rule. So the derivative of the squaring, 2y to the first, times the derivative of the inside, y prime, plus the second, y squared, times the derivative of the first, 1. So this one is 2xy y prime plus y squared. And then another product, slightly more complicated. So the first, x squared, times the derivative of the second, 2y y prime, plus the second, y squared, times the derivative of the first, 2x. Now, you could call it 2x x prime. But what's x prime? X prime is just 1. And then we could simplify this and write it as 2x squared y prime plus 2x y squared. Okay, so now we're going to get into the more complicated problems, which are more typically what you're going to do. So we were just taking derivatives of expressions, but more likely what you're going to have is actually an equation. So you have something on the left, you have something on the right. And we're going to take the derivative of both sides. When you take the derivative of y, you get dy dx, which you can also call y prime. When you take the derivative of sine 3x, you use the chain rule, you get cosine 3x times 3. So we take the derivative of both sides, and this is the full implicit differentiation process. You're given an equation, you take the derivative of both sides, and then if you are asked to, you isolate dy dx. Okay, so let's do number 1. The derivative of x squared, 2x. The derivative of y squared with respect to x, 2y times y prime, equals the derivative of 9, 0. Now we're going to isolate y prime. So subtract 2x from both sides and divide both sides by 2y. And then it reduces. Now I want to talk about this one a little bit. Do you remember what the graph of x squared plus y squared equals 9 looks like? That's actually a circle with center 0, 0 and radius 3. So let's picture that. So what we're saying is the slope of the tangent line at any point can be found by taking the opposite of x over y. So suppose I take this point right here. That point has coordinates 0, 3. So the slope at that point would be, that point has coordinates 3, 0. So the slope at that point would be negative 3 over 0, and that's undefined. And if you think about the tangent line there, it's a vertical line, so yeah, it has an undefined slope. Notice that we are now talking about the slope of a tangent line to something that's not a function. This is a relation, this circle, but it's not a function. Now suppose I took this point up here. This point has coordinates 0, 3. And for the derivative, we have the opposite of 0 over 3. So the slope is 0. And if you picture the tangent line, it's horizontal. So yes, it has a slope of 0. And we can apply the same formula to any point on the circle. Points over here, we're expecting to get a negative slope. Positive slope. Points over here, a negative slope. Down here, a negative slope. Down here, a positive slope. Now, we're not always going to analyze these graphically, but for that last problem, that was a good one to do that. Okay, here's another equation. Find dy dx. So we take the derivative of the left and we take the derivative of the right. The derivative of x to the fourth is 4x cubed. The derivative of y to the fourth with respect to x is 4y cubed times y prime, and the derivative of 1 is 0. Now we isolate y prime. Subtract 4x cubed from both sides. 4y cubed y prime equals negative 4x cubed. Divide both sides by 4y cubed, and y prime equals, reduce it, and it equals the opposite of x cubed over y cubed. This one is fairly similar to the last problem, isn't it? But it's not a circle, it's some other kind of, I don't know what object we have there. Okay, here's another one. Find dy dx. So we just keep doing the same thing, derivative of the left and derivative of the right. And with the first term, it's a product, so we're going to have to use the product rule. So we have the first times the derivative of the second plus the second times the derivative of the first. Then we move on and we take the derivative of x, which is 1. And then we move on and we take the derivative of y, which is y prime, equals, and then we take the derivative of 1, which is 0. Now, to find y prime, notice that we have y prime twice. So every term that has y prime in it stays on the left, and every term that does not have y prime in it moves to the right. So negative y minus 1. Now we have to factor y prime out of both terms on the left. So we have y prime times the quantity x plus 1. See, there's a little invisible 1 right there. And then on the other side. And now to get y prime by itself, divide both sides by x plus 1. Now it's possible that somebody would simplify this by factoring the negative out of the numerator, but it's not required. Okay, so you're taking the derivative of both sides of the equation and then you're isolating y prime. That's what you're typically going to do. We have a few more. So number 4 involves the exponential function e to the x. And if you look at this first one, you have actually to use the chain rule because your inside function is xy. So the derivative of e to the something is e to the something times the derivative of that something. So now we're taking the derivative of xy and we're going to use the product rule. The first times the derivative of the second plus the second times the derivative of the first, which is just 1. And then on the other side, the derivative of e to the x is e to the x, and the derivative of e to the y with respect to x would be e to the y times the derivative of y. E to the something times the derivative of the something. Now, once again, we see y prime in multiple places. So we need to gather all of our y prime terms onto one side and all of our non-y prime terms onto the other side. But first we need to get rid of the parentheses. So we're going to distribute e to the xy times xy prime plus e to the xy times y. I'm going to put the y first. And then on the other side, e to the x plus e to the y prime. Okay, so now that we no longer have parentheses, the y prime terms are going to go to one side, and the non-y prime terms are going to go to the other side. So I'm going to keep x e to the x y prime, subtract e to the y prime to get it to the other side. On the right, keep the e to the x and subtract y e to the xy to get it to the other side. Factor out the y prime. Got to really pay close attention to detail here. Lots of similar kinds of things being written, and then divide to get y prime by itself. And there's our answer. Now, I'm not sure that this is coming up today. It might be coming up tomorrow. There are times when you want to evaluate the derivative at a particular number. Like let's say it said find dy dx at x equals 1. Well then, and I'll tell you about this again tomorrow when it comes up, After you find the derivative of both sides, before you do any simplifying, plug in x equals 1, because it's so much more simple to simplify if you plug the number in first. I think we've seen other cases of that in different kinds of problems. Okay, so let's do this one, which has a little bit of trig in it, and it also has a couple of products in it. So we have a product right here. So we have the first times the derivative of the second plus the second times the derivative of the first. Plus, and then the derivative of xy, again the product rule, the first times the derivative of the second plus the second times the derivative of the first. And then for x squared plus 2x. And then on the other side, the derivative of 6, thankfully, 0. Okay, now we do have parentheses, but they're not holding a sum together like in the last problem. This is just a single term, and this is just a single term. Let's keep all of our y prime terms on the left. So we have cosine x times y prime plus x times y prime. And then let's get our other terms on the right. So this one here, that's a negative term. We can add it to both sides and we get y sine of x. And then this one right here, so minus y, and this one right here, so minus 2x. Factor y prime out of both of those terms on the left, and divide. I know this is a long video. Sorry guys. Sometimes that's just the way it is. Calculus can be time-consuming. Okay, I think I have maybe one more for you. Yep, this is going to be our last one. Find y prime and, hey, bonus, y double prime and triple bonus. Or is it a double bonus? Y triple prime in terms of x and y. So this is a different instruction as well. We'll get to that in a second. So let's just start with find y prime. So we'll take the derivative of both sides. We have 2x plus 2y y prime equals 0. And then isolate y prime. So 2y y prime equals negative 2x. Divide by 2y, negative 2x over 2y. And then simplify. Y prime equals negative x over y. Yay, one down, 2 to go. So we have to find the derivative of that to get y double prime. So it's a quotient. Let's use the quotient rule. The bottom, y, times the derivative of the top, negative 1, minus the top, opposite of x, times the derivative of the bottom, y prime, over the bottom squared, y squared. Now, remember how it said in terms of x and y? That means our answers can have x in them and y in them, but not any other variables. So the answer can't have y prime in it, but that's okay because we can substitute the opposite of x over y for y prime. So we have the opposite of y plus x times the opposite of x over y squared. Here we have a fraction inside a fraction, and what do we like to do when that happens? We like to multiply the top and bottom by a special form of 1 that will clear out that fraction. So we have the opposite of y squared minus x squared, because those y's cancel, over y cubed. So that's our y double prime, but there's actually something really slick we can do now if we remember what our original equation was, and we think about how that relates to our numerator. What if we factored a negative 1 out of our numerator? And I'm rearranging the order of the terms to make everything a little bit more obvious. For this problem, x squared plus y squared is 1. This right here, it's 1. So I can actually write this second derivative as negative 1 over y cubed. Oh, I like that because I have to differentiate again. Don't forget, we need y triple prime. So I'm going to rewrite this as the opposite of y to the negative third and use the chain rule. The derivative of that would be bring down the negative 3, so we get 3y to the negative fourth times the derivative of the inside, y prime. And then replace y prime with the opposite of x over y, rewrite this as 3 over y to the 4th. And we have negative 3x over y to the 5th. So what at first looked like it could be horrible was actually only somewhat awful. I like it when that happens. Sorry, speaking of somewhat awful, for having a 25-minute video. Here's your assignment, and tomorrow we do more implicit differentiation. Thanks, everybody.